And so we're going to look a little further into what we're doing with these chemical bonds. And the first thing they go through as an example in your textbook is just, it says, how can we take two poisons, elemental sodium and elemental chlorine, and then we combine those two, sodium and chlorine, to make sodium chloride that we can put on our food, which is not, poisonous at all. And basically how that is between the exchange of electrons that stabilizes the atoms of both those elements, and it makes a chemical bond in the sodium chloride. So it takes sodium as a solid plus chlorine gas and makes NaCl, which is a solid. Oops. Okay, so if we look at I went two slides, sorry about that. We're not going to talk a lot about Lewis structures, but G.N. Lewis, Dr. Lewis, is the person who discovered the bonding and what valence electrons were. And he is the one that started with the two different bond types that we've been talking about. Ionic, where the valence electrons are transferred, and covalent, where our electrons are shared. So we've already been talking about that. Okay, and that occurs because of filling the outer orbits, and they call those the Bohr orbits. And I don't care if you know that, but that's what we've been trying to do. Remember the octets that we were talking about. And again, this is called the octet rule because the stable configuration involves 8 electrons in that outer shell to make it stable. Okay, so this is what it would look like if we were to draw the Lewis structure here of an elemental symbol. And this is silicon, and we've got the symbol surrounded by the number of dots equal the number of valence electrons. So if we look at silica in the dark on our chart, you can see it's in column 4, so it's going to have 4 electrons, 4 valence electrons on the outer shell. So we don't really look at what's on the inside. We always look at what's on the very outer core, because those are the electrons that are going to either be transferred or shared. Okay, so that's all we care about is that outer shell where we've got the 4. And I know that's hard to see from here, but it's got a 4 electron on there. So basically, the chemical bonding brings those outer shells together so that they can become an octet. So that's what we've been doing with making, the charges go to 0. We've been making them form either an ionic bond or a covalent bond by either having metals or nonmetals, and we're putting them together. So that's what happens in the real world. We just haven't been drawing these Lewis dot structures. Okay, so when we look at ionic bonding, we have the transfer electrons from a metal to a nonmetal, and this is what it looks like in moving dots. So if we look at sodium, which is in the first column, because it has 1 dot or 1 electron, you get 1 dot here. Okay, with chlorine, if we look at it, it's in column 7, right? So since I have an octet rule, I can have a possible of 8, so I've got 1, 2, 3, 4, 5, 6, 7 dots because I'm in column 7. So all they're doing is putting dots up here instead of, to show you how they go together. So what happens is this 1 electron from sodium goes over here to chlorine and fills it in. Okay, so we've got the plus and the minus, and that becomes uncharged when the plus and the minus come together. So I've just decided that we're not going to draw all these dots this year to go through it, but I want to understand how the electrons go together. Okay, so this is just another explanation of what we've been doing with the ionic and covalent bonds. So the metal and the nonmetal are each going to acquire a charge in the formation of an ionic bond. Okay, so we put the charge, as we've already been doing, in the upper right, so we don't confuse it with our subscript. Okay, when they're doing the Lewis structures, we usually put the brackets around here so that we make sure that it's all included in that charge. And again, the charges on anions and cations have to sum to 0 when I put the compound together. So again, we're just going back through another way to confirm how we're going to get this an ionic bond formed or a covalent bond formed. Okay, so we'll just show how calcium oxide would be drawn in a Lewis structure. Okay, calcium has the 2 electrons there on its bond. It's a metal, so when it forms ionic bonds, it's going to lose both valence electrons. Oxygen is a nonmetal. Okay, so it's going to need something to get its other 2 electrons to become a stable form. So basically, it will take the electrons from calcium and we get calcium oxide. So Ca becomes a +2, oxygen is the -2, and then we see that it becomes a 0 charge by balancing out. So we don't really write the charge on it. So that's really what we've been doing this whole time in balancing ionic forms, or ionic compounds. With the covalent bond, remember we said a covalent is with no metals in it at all, and they are going to be sharing electrons. So they're showing you chlorine, which is in column 7, so it has, is it not? Somebody going to confirm that for me? Yes? No?
Yeah.
You asleep? Okay. Just want to make sure I still had you with me. Okay, so it has 7 outer electrons. So basically this has 7, this has 7, and those 2 come together and they're going to be shared. Okay, so those will be going back and forth. So it counts as the octet for more than one atom. Okay, so that's how that stays bonded together. Okay, when we're looking at these electrons, they're called bonding pairs, and electrons on a single atom is a lone pair. So these are the bonding pairs because it's holding these 2 atoms together. But when I have a full shell and I have them out here, they're called lone pairs. And these are the only ones that count towards the octet of both atoms, are the ones that are in the middle holding them together. Okay, and the main reason that we're looking at some of these structures is so we can see what the physical structure of these bonds look like. And when we look at hydrogen and oxygen coming together to form water, it's a 2-to-1 ratio of hydrogen to oxygen. So we have to have 2 hydrogens for every oxygen because oxygen has 6 electrons on the outer side, so I have these 2 pairs here and then a single one here, so we get a hydrogen that bonds with it on both sides of it. Okay, and there's also, when we look at these, as we look at structures, sometimes those multiple bonding pairs are necessary to complete the octet. So I might have a double bond, okay, for each atom in the Lewis structure. So the 2 bonding pairs together are a double bond, 3 bonding pairs are a triple bond. Okay, the reason that we're talking about this is because if I have a double bond, it's going to be harder to break, it's going to take more energy. If I have a triple bond, that's going to be harder to break as well. And in structures, the more bonds I have, it's got to stay straight, it can't bend. A single bond can bend and have angles to it, which is how we get some of our structures that we're going to be talking about. And in a couple labs, we're just going to sit there and play with what I like to call tinker toys and look at all the bonds and just see how they might form, but we're not going to do that quite yet, okay? Okay, so if we had to look at this particular structure, what am I looking at? I've got NH3. So I've got ammonia. Okay, so if we look at nitrogen, and I apologize for being in the dark again. So we look at nitrogen, it's in column 5, so I'll have 5 outer electrons, which means I'm going to have 1 lone pair, and then I'll have 3 electrons on the outside here. So that means that I could have, with hydrogen having one electron, I can put hydrogen on each of those 3 corners. So basically, that's why I get an H3 forming, is I can put those atoms on as possible. Okay. If I have a nitrogen on its own here, okay, which nitrogen again has the 5 bonds. If I don't have anything else to bond to it, then it's going to put, if I need 3 more bonds, it's going to put the triple bond in the middle to itself to fill up those shells. So it explains how you get an N2 and why it does this if it's on its own, because basically it wants to be stable. Okay, so they asked us to draw the structure of CH4, and if we look at carbon, where is my carbon? Carbon is in column 4. Oh, I put it behind the screen, didn't I? So if I'm in column 4, I have 4 valence electrons. Okay, so it wants me to draw CH4, and H has 1, so I can put an H here, right? An H here, an H here, oops, and an H here, just like it has on the slide.
So,
Okay.
Gwen?
Yes, can you see that?
Yeah, I can see it.
Oh, okay.
Oh. So is that considered a covalent bond?
What did you say? Carbon, hydrogen?
Well,
Carbon
hydrogen, yes.
and hydrogen.
Since it only has one, you have to share. You have to.
So it's you're saying it's covalent bond?
Yes, because it's a carbon and hydrogen. There's no pluses and negatives going back and forth there. It's sharing.
Right.
Because this has 1 and that has 1.
Okay.
This has 1 and that has 1, and it's got to go back and forth.
Yeah. So
Does that make sense?
Yeah, it does.
I know it's a little hard.
So I was gonna ask you though, like,
Yeah.
if there was a physical difference between sharing and transferring electrons. I guess that's just showing the difference between positive charges coming together or a positive and negative charge.
Well, yeah, because basically you can't with a nonmetal you don't have the positive and negative there. So I don't have the positive and negatives going together. I have to. They're just sharing. They're not They're not actually transferring electrons. They're just sharing to keep it stable. So it's going back and forth like this. It's not a positive and negative charge.
If it's physical, it would have to, one electron shell would lose one valence and so on. So one would become smaller compared to one would become bigger, being stable, because it would fill that electron.
So with the ionic, they're actually taking one electron and putting it in the other shell, and the other's losing it, and it's like he just said, they're actually becoming physically stable. And these are just, they come together and they share back and forth, so there's no change in the actual electron shell. We'll think about it a little bit longer, okay? And I'll think of a better explanation, because I can see I'm not getting through to you, and I'm trying to think of how else to explain it, and it's not coming out right.
Okay.
But it's the difference between the
Maybe
positive.
I just shouldn't have asked.
No. I'm just not. It's not coming out correctly today, so I'll find a better explanation so that you understand. But the difference is because it doesn't get a positive and negative charge on it because it's not ionic.
Well, hydrogen, it can't lose one, otherwise it doesn't have any, so that would mean it would just break up for the protons and neutrons.
Okay, so there is a physical difference between transferring and sharing
Yes.
electrons.
Yes.
Okay.
Yeah, because it's when
So
you transfer, you're actually moving it over to that molecule.
Another one that doesn't have any valence electrons. The one that lost its electron.
It would have to go down to the next.
It'd go
It'd
down
go
to the
down
next.
to the
It'd go
next.
down to the next shell.
Shell.
Which actually would make it positive, which will hug the electrons even closer compared to the one that gained one, which has a little bit less charge, so the electrons will be further out from the actual element. So it's basically with charge and so on.
You can see why I didn't go into Lewis structures before, but basically, you're either sharing it and keeping them together, so they go back and forth, so they don't change, or like he said, If it goes over to the other one, it becomes bigger, and the other one's going to lose its outer shell. But it still holds together. You're having trouble with what it looks like and what it. I can see what's going on in your head.
It has a positive and negative
Yes.
charge,
That makes
which
more sense.
subtracts it.
Okay,
Okay.
it's getting there, but not there. I can tell. All right, we'll go through some more here. I didn't explain it well enough. I can tell. Okay, I didn't want to go into the two of them together. Okay, let's look at what we hear a lot about out in the atmosphere. Let's look at chemical bonding in ozone. So ozone is that gas that protects us from UV light. Okay, so if we look at ozone molecule, ozone is an O3. Okay, so ozone molecules in the atmosphere are going to absorb the ultraviolet light so that we don't get sunburn. Although we still do, right, because of holes.
Radiation.
Pardon me?
More radiation.
Right. So if we look, and this is getting more into what I'm probably going to really confuse you with this. So basically with ozone, we have to have a double bond when we put the other oxygen in. But basically it kind of shares the bond, so each one's shorter than a single bond, but longer than a double bond, so it comes together differently. So I think what I'm going to do is stop here with that until I can explain it better, because it's gonna basically look like this. So we've got, it doesn't quite have a double bond; it's somewhere half in between for the oxygens. Right, it does, and so they put an arrow between it. So I think I'm going to stop here with this one, and I'm going to get a better explanation for the bonding on that before tomorrow. So let's stop here, and what I do want you to do, though, is to finish looking